Welcome back to Basic Biostatistics 2, to session number 9 about logistic regression models. The learning objectives of these sessions are to learn to run a logistic regression model, to understand how to construct the best model and how to see whether the odds ratio was confounded by other variables, to get familiar in interpreting the findings of the logistic regression analysis in SPSS, and basically how to check for efficiency of the model or for goodness of fit of the logistic regression model. As any other models, logistic regression models try to predict an outcome based on several predictors, one or several predictors. For instance, if you would like to know whether BMI is associated with type 2 diabetes, we can run a logistic regression model. The important thing is in logistic regression that the outcome variable is dichotomous. It means it's a categorical variable that has only two outcomes, yes or no, having the disease or not. The independent variable, however, that can be continuous or categorical. The important and the nice thing in logistic regression analysis is that the independent variable, if it's continuous, does not have to be normally distributed. So we really don't care about normal distributions in logistic regression analysis, because the mathematical equation takes the logarithm of that continuous variable. That means that if you use a logarithm, most likely distribution follows a normal distribution. The categorical variable can be dichotomous or can have several categories, so we do not have any problem with that. This makes logistic regression analysis pretty easy to conduct. Where can we find logistic regression analysis on SPSS? We go to Analyze, and here we have Regression under Correlate, and we scroll down to Binary Logistic. We click on Binary Logistics, and we have the logistic regression window open. In our study hypothesis is we would like to know whether we can predict diabetes according to BMI categories. So I select diabetes status of our dwarfs from the left hand side and move it into the dependent window. And now I select the covariates, that is our independent variable, that is a BMI category, and I move it to the covariate window. Two things left I have to do before I can click on OK. First of all, I have to tell the program which of our independent variables or covariates are categorical. BMI is categorical, so I select BMI in category and I move it into the categorical covariates window. As you can see, SPSS has defined the contrast. Contrast as a reference category means that to which category we compare. I suggest you always to use the first as the reference category. In order to change that, we have to click on first and on change. Now you see here at the end of the BMI category indicator, it's written first. That means that our reference category are the normal weight dwarfs, as this was the first category we have. So everything will be compared against our normal weight dwarfs. We click on continue and we go to options, and under options I usually choose the Hausmann-Lemeshoff goodness of fit test that tells us whether we have a good model, and the confidence intervals for the odds ratios. As you probably remember from Basic Biostatistics 1, logistic regression analysis provides you the results as odds ratio or as odds. If you want to know more about odds, please go to the readings of this chapter or go back to Basic Biostatistics 1, where you can learn what's an odds. We click on continue, and that's basically it. Then we click on OK, and SPSS gives us several windows. This is the output file you're going to see. We do not have to interpret all the tables. I give you a short summary of what's the important findings. Again, we have case processing summaries. We have here the variable BMI categories. It tells us that it's 17 observations with normal weight, 29 observations with overweight, and 14 dwarfs that have obesity. It runs as first information for block 1. Block 1 means that we do not have any independent variable model. And the 50% you see here, the overall percentage, mean that Without knowing the BMI category of our dwarfs, we have a 50% chance to predict whether the dwarfs have diabetes or not. It's a 50-50% chance because we have 30 dwarfs with diabetes and 30 dwarfs without diabetes, so just by guessing, you are 50% correct. It also tells us that the constant in this model will only have the constant in the equation without the independent variable, and it also gives information about the variable that was not in an equation, which is BMI category. You can basically omit the information of block 0 because it's the first step the SPSS runs for the statistical of the logistic regression model without adding the independent variable. Now, block 1 means that method enter means now the SPSS has added our independent variable BMI category into the statistical model. You can see that the omnibus test of molar coefficient is statistically significant. We can step block model, we can choose any of these p-values. They're below 0.05. This means that we have a statistical significant model. So the omnibus test of molar coefficients tells us whether our model is statistically significant. It doesn't give us yet any odds ratio, it just tells us we have a significant model. The next table from the model summary gives us the Cox-and-Snell R-squared test or the Nagelkerke R-squared test. You can choose any of those two R-squared tests. The R-squared test, the interpretation is similar than the multiple linear regression models. The bigger the R-square, the more complete the model. Our model has an R-square of, if you choose Nagelkerke, of 45%. Is pretty high considering we have only one variable in the model. The next is the Hosmer-Lemeshoff test we selected. The Hosmer-Lemeshoff test is a test, a goodness of fit of our model, whether we have a valid or a good model in general, independently if it's statistically significant or not. The null hypothesis of the Hosmer-Lemeshoff test is that our model is a good fit. If the p-value is bigger than 0.05, this means we have a good model. If it's smaller than 0.05, we do not have a good model, and this means the odds ratio we've received are most likely inflated. In our case, the p-value is much higher than 0.05, it's exactly 1. This means we have a good fit, we have a good model. It gives us then a contingency table for the Hosmer-Lemeshoff, we can omit that. We scroll down then actually to the table, classification table, where we see now adding BMI category to the model, we can now 75% of the cases we can predict whether our dwarf of Santa Claus has diabetes. So the increase from 50 to 75%. The last table is our most important table, our output table, where we can see the odds ratio for the different category of BMI. BMI cat with the normal weight is our reference category, and then we have two more categories, overweight and obese. B is basically the slope. What we are interested is in the odds ratio. In SPSS, the odds ratio is given as XB, exponential B, and we can see that the odds ratio for overweight is 22.667. This means that compared to normal weight dwarfs, being overweight increased the risk of having type 2 diabetes by 22.667 times. Our confidence interval is pretty large. It ranges from 2.6-fold increase to 194 times increase of the risk of diabetes if our dwarfs are overweight. In case our dwarfs are obese, we have a 96-fold increase in risk of having type 2 diabetes, with a large confidence interval as well. If the confidence interval is large or wide, it means the precision is not very high. Now, are these confidence intervals or these odds ratios statistically significant? Well, we look at the confidence interval. If they do not cross 1, of the same side of 1, they're statistically significant. In our case, they're statistically significant because we know that the risk increase at least 2.6 times, maybe even 194 times. You could also look at the p-value. It gives you the same information that the p-value is lower than 0.05, which means the odds ratio is statistically significant. Our conclusion would be Yes, BMI categories is a predictor of type 2 diabetes. Now, in logistic regression models, we like to adjust our analysis for several other covariates. We may think that, well, okay, BMI may be confounded by some other factors. Maybe age, maybe educational status could be a possible confounder for our association observed between BMI category and type 2 diabetes. Where can we add other variables and other covariates for our statistical analysis? We go back to analyze and we go back to to regression models and to binary logistics. As you see, we still have BMI category selected in our model, our dependent variables diabetes mellitus, and here we have all other variables. Now, what could be possible confounders of the association between BMI category and diabetes mellitus? Well, we know that maybe age of the dwarfs may have an impact. Maybe age could be associated with the BMI category and age could be associated with diabetes. So I choose age as a continuous variable as a covariate. This means that our analysis will be adjusted for age, or the association between BMI category and diabetes mellitus will be adjusted for age. If you go to the categorical window, you see now we have age as a covariate. However, age is not a categorical variable, so we do not have to take any actions in this window. So we click on continue. Under options, we still have the Hausmann-Lemeshoff test selected and the confidence interval. We click on continue and on OK. As we have added now a first covariate or the first possible confounder, we basically get the similar Windows output. We scroll down, we check the Hausmann-Lemeshoff test. It's 0.38, which means it's still statistical not significant, which means we have a goodness of fit. The Nagel-Kerkegaard square test now increased from 0.45 to 0.52, so we improved the completeness of the model. We have a model that is still valid, we have a model that is more complete than the previous one, and we still have a significant model as we have a look at the omnibus test of model coefficients. Now when we scroll down, we see now the odds ratio have changed. We have now a different variable, an additional variable in the table, which is age, as we include age to the category, and we see basically age is as well statistically significant, even that probably doesn't have much clinical relevance. We see the p-value is significant, the risk for one increase of 1 year of age, the risk increase of diabetes 1.002 times. How can we know whether age was a confounder of the association between BMI category and type 2 diabetes? We can see it from the change in the odds ratio. If the odds ratio from the previous model to this model changed more than 20%, then age was a confounder, and this would be a reason why to leave it in a model. BMI category for the overweight was before that 22, now it's 29. This is definitely more than a 20% increase in the odds ratio. So we will claim that yes, age was a confounder of the association between BMI category and type 2 diabetes. So we better leave it in the model. In order to find out other confounders for the association between BMI category and type 2 diabetes, we would now need to add one variable at a time. If you add a third variable, you check whether the odds ratio changed from BMI category for the overweight and obese. If the odds ratio changed by more than 20%, then we have a confounder and we leave the variable in the model. If the variable does not change the odds ratio, then we remove it from the model. There's a way how to do it in logistic regression using stepwise regression. However, I do not recommend using stepwise regression, but do it manually. Add one variable at a time, remove one variable at a time in order to find the best model that predicts BMI category and type 2 diabetes. Thank you very much. Enjoy the exercises and the quiz.